Can electricity create magnets? Let's uncover the hidden power of electricity in Chapter 4.
Welcome back. Today we're diving into another explainer, and this time we're tackling one of the absolute coolest, most invisible forces in the entire universe. We're going to start small, with a basic tabletop experiment you could totally do in your kitchen. But by the end, we are literally zooming all the way down into the swirling, molten core of our own planet. It's a pretty wild ride connecting electricity and magnetism. So let's just jump right in.
Let's kick things off with Section 1, Magic at the Science Fair.
All right, so picture this. You're at a super bustling middle school science fair, and two students, Mohini and Akarsh, are wandering around. They stumble across this really awesome working crane model built by a senior named Suman. Now notice what the crane is picking up. Yep, just standard iron paper clips. But here's the kicker. Look closely at the crane's hook. It's not actually a regular permanent magnet. It's literally just an ordinary iron nail with some flexible wire wrapped around it, hooked up to a standard battery. But when Suman flips the circuit on, boom, the nail acts exactly like a super-powered magnet and picks up the clips. And the second the power gets cut, they all drop. As you can imagine, Mohini and Akarsh are totally blown away.
So the big question here, right? How exactly does this wire and battery become a magnet? Now, we all know from basic science classes that magnetic materials like iron stick to magnets, but there's no actual magnet in Suman's model. It's just a regular old electric circuit. So how does a totally basic electric circuit suddenly get magnetic superpowers? Well, that's the main mystery we're unpacking today.
Which brings us to Section 2, the magnetic effect of current.
Okay, to really wrap our heads around this, we need some visual proof. Check out this setup. Over on the left, we've got a super basic circuit. Battery, some wire, and a switch made out of a regular safety pin. And right underneath that wire, there's a small magnetic compass. Right now, the circuit is open, the switch is off, no current is flowing, and the compass needle, totally still. But look over at the right. The safety pin is closed, the circuit is complete, and the literal split second that current starts flowing through the wire, bam! The compass needle violently deflects from its resting spot. And as soon as you stop the current, it snaps right back.
What we just saw there is actually mind-blowing when you think about it. It proves that whenever an electric current flows through a conductor, like our wire, it literally creates its very own magnetic field right around it. That compass needle, it wasn't reacting to a hidden magnet somewhere, it was reacting to the invisible magnetic field generated by the electricity itself. We call this phenomenon the magnetic effect of electric current.
Let's dig into how we actually found this out in Section 3, Ørsted's historic discovery.
So, let's rewind the clock a bit. The wild thing is, that exact same realization we just had looking at the compass, a Danish university professor named Hans Christian Ørsted had that exact same aha moment over 2 centuries ago. He was the very first person to figure out that electricity and magnetism weren't just separate things. They were actually intimately connected. The year was 1820, and the story goes that Ørsted was actually right in the middle of giving a live lecture demonstration when he caught something out of the corner of his eye. Every single time he turned the electric current on or off in his setup, a compass needle sitting on the table just casually twitched. He got obsessed, tested it meticulously, and published the groundbreaking discovery that electric currents create magnetic fields. I mean, talk about a happy accident, right? This one little observation literally changed the course of global science forever.
All right, let's get hands-on with Section 4, making an electromagnet.
Let's shift gears and actually build one. It's shockingly simple. Step 1. Grab about 50 centimeters of flexible, insulated wire and just wrap it super tight around a regular iron nail to make a coil. Step 2. Slap some tape on those coils so that they don't unravel on you. Step 3. Connect the 2 bare ends of your wire to the positive and negative terminals of a standard battery. Now, quick safety disclaimer from the source text. Definitely do not leave it connected for more than a few seconds at a time, otherwise you'll drain your battery incredibly fast. And ta-da! Here is the actual result. The electric current flows right through that coiled wire, generating a magnetic field. But here's the genius part. Because we wrapped it around an iron core, the nail, that core becomes magnetized too. This makes the overall magnetic effect incredibly strong enough to effortlessly snatch up those heavy paper clips. You, my friend, have just created a practical temporary magnet, the classic electromagnet.
Now notice how this electromagnet behaves exactly like the permanent bar magnets you played with as a kid. If you bring a compass near one end of our coil, let's just call it end A, the north pole of the compass needle will point right at it. That means end A is acting as a south pole. Check the other end and it's the exact opposite. It has a true north and south pole. But want to know the craziest part? If you simply swap the battery connections to reverse the flow of the electric current, the poles of your electromagnet actually flip. Moving right along to Section 5, increasing the magnet strength. Okay, so maybe you're thinking bigger. What if we want to build, say, a massive industrial crane that lifts literal tons of scrap metal instead of a few tiny paper clips? Well, there are two main ways to seriously crank up your electromagnet's power. First off, just increase the number of times you wrap that wire around the core. More coils literally equals a stronger magnetic field. Second, you can pump way more electric current through the wire by increasing the battery power, say hooking up 2 or 3 cells instead of just one. Pushing a stronger current instantly generates a much more robust field. Tweak those two factors and you can scale this effect up to incredible levels. Now for my favorite part, Section 6, Earth as a giant magnet.
All right, we've totally mastered the tabletop stuff. Now, let's zoom out, like way, way out. Just let this sink in for a second. Our entire planet acts exactly like the little electromagnet we just built. Deep, deep down inside the Earth, there is a core made of incredibly hot, swirling liquid iron. And as this liquid metal constantly churns and moves, it generates colossal electric currents. And just like our guy Ørsted discovered, wherever there's an electric current, a magnetic field is born. So yeah, our Earth is quite literally a gigantic, spinning electromagnet.
And honestly, thank goodness it is, because this planetary magnetic field is absolutely vital for us. You know how a compass needle always points north? That's just it aligning with Earth's massive magnetic field. Countless migrating birds, fish, and other animals rely on this invisible global grid to navigate across thousands of miles of oceans and continents. But even more crucially, this giant magnetic bubble surrounding our planet acts as a literal shield. It actually deflects incredibly dangerous, highly energized space particles, stopping them from just bombarding the surface of our world.
Which really leaves us with this pretty wild thought to wrap up our explainer today. We started off just looking at a simple wire, a battery, and some paper clips at a school science fair, but understanding how those tiny moving electrons create an invisible magnetic force, it brings us to realize that the exact same phenomenon is happening thousands of miles beneath our feet. Seriously, without Earth's giant protective magnetic shield, would life as we know it even be possible? It is pretty incredible how a concept as simple as electricity flowing through a wire is quite literally what protects our entire world. Thanks so much for joining me for this explainer, and keep exploring.
Welcome to today's explainer. I'm so glad you're joining us because we're about to decode one of the absolute most fundamental forces powering our world. We're going on an incredible journey today. We'll be exploring everything from the massive industrial machines that effortlessly lift tons of solid steel, all the way down to the tiny, unseen microchemistry happening inside a common, everyday lemon. It's a story of invisible forces, and I can't wait to share it with you. Okay, let's dive into this. Here's our roadmap for today. We're going to cover the magic of electromagnets, why wires get hot, heat in our homes, the chemistry that creates electricity, the wild story of the first battery, and finally, our rechargeable future. All right, part 1, the magic of electromagnets, moving massive weight. You know, we usually just think of electricity as the stuff that turns on our lights, right? But it can actually create insanely powerful magnetic fields. Take the lifting electromagnet. This is definitely not the magnet holding up your grocery list on the fridge. It's a massive piece of equipment attached to a heavy-duty crane. But the really wild thing here, its magnetism isn't permanent. It literally only becomes a magnet when an electric current is actively flowing through it. Think about the sheer practical power of that. In a massive factory or a scrapyard, a crane operator has this absolute precise control over literally tons of heavy metal. They just flip a switch, electricity flows, and boom, the electromagnet instantly grabs heavy iron and steel objects. They move the crane to where they need it, flip the switch off, the current stops, the magnetic field vanishes, and the metal drops instantly. It honestly looks like magic, but we're really just manipulating a magnetic field on demand. Moving on to part 2, why wires get hot, the power of resistance. So we just saw electricity acting like a magnet, but what happens when its physical path changes? Well, that changes the whole game. Here's a classic setup to demonstrate electrical resistance. Notice how, instead of just using normal copper wire to connect the two ends, we're specifically using a 10 centimeter long, 0.3 millimeter thick piece of nichrome wire. Let's imagine walking through this little lab experiment together. First, you hook that nichrome wire up between two nails on a board. Then, you flip the switch and let the current run for just about 30 seconds. Finally, you turn the switch off and, very carefully, touch the wire. What do you think just happened? Well, if you touched it, you'd immediately feel that the wire got hot, like really hot. But why? It's all because of electrical resistance. As the electricity tries to flow, it faces friction, resistance, and nichrome pushes back way harder than standard copper. All that resistance forces some of the electrical energy to physically transform directly into heat energy. And this isn't random. It's affected by a few specific things: the material, the wire's thickness, its length, and how long you let the current flow. Honestly, if we slapped a second battery cell onto this circuit, the heat would shoot way up because we're pushing even more current through. Which brings us to part 3, heat in our homes, daily applications. Now, you might be wondering, why does this matter outside the lab? Well, let's look at your morning routine. A glowing room heater or your electric iron? They are purposely built around a heating element or coil. They intentionally use highly resistant wires, just like that nichrome we talked about, to turn electrical resistance into heat. So you stay warm, and your shirts stay crisp. It's the exact same principle when you boil water in an electric kettle or dry your hair. They rely entirely on calculated resistance. But here's a quick safety reality check. Because this resistance generates such intense heat, if too much current flows through your home's circuits, it can literally melt plastic plugs and sockets, or way worse, spark an electrical fire, which is exactly why we have safety devices built right into our home's circuitry. And when you scale this concept all the way up to the industrial level, it is absolutely mind-blowing. The exact same physics boiling your morning tea are used in massive, high-temperature electrical furnaces. These industrial giants use extreme electrical resistance to generate enough heat to completely melt down and recycle solid scrap steel. Okay, part 4, chemistry that creates electricity. We've looked at magnetism and heat, but how on earth do we store or generate this current in the first place? Well, it all comes down to chemistry, and this simple voltaic cell perfectly illustrates the whole shebang. To chemically create an electric current, you really just need 2 things. First, 2 plates made of different metals, we call these electrodes. Second, you submerge them in a liquid called an electrolyte, which is usually just a weak acid or a salt solution. The chemical reaction between those metal plates and the liquid is what actually generates the electricity that flows through the circuit. Part 5. The first battery story, a scientific duel. To really appreciate this, we have to rewind to the late 1700s. The invention of the battery actually comes from a highly dramatic and kind of bizarre scientific rivalry. In one corner, you had Luigi Galvani. He noticed a dead frog's leg kicked when he touched it with 2 different metals. He actually thought the electricity was coming from the frog itself. He literally called it animal electricity. But in the other corner, Alessandro Volta was totally skeptical. Volta proved the frog was entirely irrelevant. He showed the electricity was actually coming from the reaction between the 2 metals and the salty fluids inside the leg. By swapping the frog out for paper soaked in salt water, he proved his point and invented the very first battery. That's exactly why we call them voltaic cells today. And the coolest part, you can totally recreate this late 1700s magic in your own kitchen right now. You can replicate Volta's legendary discovery using just normal acidic fruit from the grocery store. Just grab 5 juicy lemons, stick a copper wire and an iron nail into each one, connect the copper of the first lemon to the iron of the next to make a chain, and then hook the 2 final ends up to a little LED bulb, and you get this amazing result. The LED actually lights up. In this little setup, the acidic lemon juice acts as our electrolyte, while the metals, the copper wire acting as our positive electrode, and the iron nail acting as the negative, react with that juice to generate a real, measurable electric current. Finally, Part 6, the rechargeable future. So, taking a huge leap from frogs and lemons, let's talk about how we use these chemical reactions today. Mostly, we deal with 2 types of batteries. First up are dry cells, your standard single-use batteries. Once the chemicals inside are used up, their life cycle is over and they have to be safely thrown out. But then we have the absolute marvel of rechargeable batteries. These are the guys powering our phones, laptops, and electric cars. They can be re-energized and reused over and over. But even they aren't immortal. With constant recharging, the chemical components inside slowly degrade over time, which is exactly why, after a couple of years, your phone just doesn't hold a charge like it used to. So, as we wrap things up today, I want to leave you with this thought. Every single time you flick on an electric kettle, watch a crane in a scrapyard, or just send a text from your phone, you are harnessing this incredible dance of magnetism, heat, and chemistry. Since our modern lives rely entirely on this unseen resistance and ancient chemical reactions, how will our understanding of electricity shape the incredible innovations of tomorrow? I'm willing to bet you'll never look at your toaster, your phone battery, or even a simple lemon the exact same way again. Thanks so much for joining me on this explainer, and keep questioning how the world around you works.
Thanks for watching. Keep learning, keep exploring science. See you in the next chapter.